All right, welcome to part 3 of our snow day lecture. We're going to finish off chapter 2 talking about Earth's layers. All right, so here's a diagram that you've seen in your text, and I just want to highlight some aspects of this. So let's start in the center of the Earth and look at the core. Okay, so the composition of the core is iron and nickel. The core has very high temperature, very high pressure. I'll go over here, inner core, this part here, here's the outer core. This outer core is partially melted. Okay, so the inner core, high pressure, it's solid. Outer core is partially melted. The question is, how do we know it's liquid? Well, to know that, we have to realize we have to have empirical evidence, right? We're going to do good science. We need, did I get it spelled right? Yes, I did. So we need empirical evidence that there's liquid. And so the way scientists look at this is by looking at earthquake waves or seismic waves. When an earthquake happens, it sends waves through the earth, similar to how when you throw a stone onto the surface of water, it sends waves over the surface of the water. So we know that it's water because we can see those waves. Well, in the case of the Earth, when the seismic waves are passing through the Earth, they don't travel through liquids, but they do travel through solids. And so by looking at how those waves travel, we can tell which parts in the inside of the Earth are solid and which ones are liquid. Okay. Also, we should note that the movement of melted material inside the Earth is producing the Earth's magnetic field. Okay, so iron in the Earth is magnetic. And when it's flowing here in the outer core, this produces a magnetic field. Similarly to how we have magnetic fields on the sun, right? We had differential rotation, we had movement of charged material that gave us the sun's magnetic field. Well, the same kind of movement of material is happening inside the Earth, giving us our magnetic field. All right, let me take this off. And let's go out to the mantle. Okay, mantle has a different composition. So we had iron and nickel in the center. Now we have oxygen, silicon, and magnesium making up the mantle. And that's shown here in gray on the Earth. That gives you kind of a rough idea of how big it is. The mantle, again, is solid. But it's hot. Okay, so it's close to the melting point of the rock. Because it's close to melting, it flows. Okay, so it's hot enough to slowly flow even though it's not considered molten. In the upper mantle, we have this asthenosphere layer, and that's sort of shown here. So up here near the top of the mantle, and this is called, they identify it as a plastic layer. So plastic, as a material, can be sort of soft and flexible, but yet it's still solid. And so that's kind of how you can think about this layer in the upper mantle. It's a layer of weak rocks and it can deform like plastic. And then on the outside of the Earth, we have the crust. We have oxygen and silicon being the primary components of the crust. Again, the crust is solid. That makes sense. It's the part we walk on, right? And in the crust, we have the lithosphere. Now the lithosphere, on this diagram up here, you can actually see, it's composed of both the crust and the top part of the mantle. The defining feature here is that this is the rigid place. Okay, so this is all very solid. It's not deformable like this plastic layer in the asthenosphere. The crust then and the uppermost mantle of the lithosphere are broken up into tectonic plates. And we will talk about that later on in the week when we meet together again. And we'll talk about exactly what are these tectonic plates and where are they. So I want to sort of distinguish between these two ways of looking at the Earth's layers. So one way would be compositional layers. These are the layers that are defined by their composition. So this is the core, the mantle, and the crust. So each one has its own kind of composition. And then we have the functional layers. And these are the layers defined by how they act. Okay, so we have the asthenosphere. And this is the one that's kind of flexible, the movable. And the lithosphere, this is the one that's rigid. Okay, so even though the lithosphere is composed of both mantle and crust, we can think of it in terms of its overall function, and that is to have this rigid structure. Okay, and then the asthenosphere is part of the mantle, and this is that flexible part that allows things to move. Okay, and we'll say more about that on Wednesday when we talk about plate tectonics. All right, so let's do a little bit of scientific reasoning. We'll look at a geothermal gradient. How does the temperature change within the Earth? Well, I mentioned on the last slide that in the core, you have very high temperature, very high pressure. And this is residual from when the gravity pulled Earth together when it was first formed. Okay, so there's this residual heat that's inside. But as you know, on the crust where we live, it's not as hot, right? So there's a temperature change that happens sort of between here and there. So let's look at these diagrams. There are 4 possible diagrams to describe the Earth's geothermal gradient. So let's kind of analyze these. And I want to ask, which plot best describes our present day gradient? So here we have space. So we have the surface of the Earth. Okay, this is the top of the crust. And I'll just make a note here, crust. And then down here, the interior, this would be in the core. Inner core, outer core. It doesn't matter too much. These are very schematic diagrams. Okay, they don't have the exact numbers. They give us the general trends. All right, so as we go from the surface down, what is the temperature doing? Okay, so each of these options shows going from low temperature to high temperature. So low to high, etc. Okay, so how does the temperature where we are change as you go down? Well, we're in a low temperature situation, and as you go into the center of the Earth, the temperature gets higher and higher and higher. So which of these diagrams corresponds to that? Well, let's look at A. Here on the surface, we have low temperature. So this makes sense, right? The surface has a low temperature. As you go further in, your temperature gets higher and higher and higher. Okay, so A is actually a really good answer for this. If you know, the opposite effect over here with C, here you have, this is saying that the temperature at the surface of the crust is very high and that it gets colder and colder as you go down. Okay, that doesn't make sense. Cross that one off. All right, so let me ask you this now. Which plot best describes the gradient, what it would have looked like 2 billion years ago? All right, well, in the Earth's geologic past, would you still expect the inside to be hotter than the outside? Well, yeah, based on what we know about how planets and stars and all beings form, the inside is in general going to be hotter than the outside. So that means for this one, we can rule out C. We can also rule out D, right? Because this line is sloping the wrong direction. So the question is the best answer for this question for 2 billion years ago, is that going to be A or B? Is the Earth's temperature the same now as it was 2 billion years ago? My hypothesis would be no. And here's why I would suggest that. Because the Earth is cooling down over its geologic time. The center of the Earth is gradually getting colder and colder. Now we can't observe those changes on Earth because it's a billion-year process, and so over the time that we're observing the Earth, we can't observe this. But we can make a hypothesis based on what we know now that probably 2 billion years ago the Earth's crust was warmer than it is now. Okay? So if we look at, we still have a lower temperature getting higher as you go into the center, but it's not as low 2 billion years ago as it is now. Okay, so that's why B is the best answer for this, because 2 billion years ago we expect the surface to be hotter than it is now, but still have this same trend of higher temperature as you go into the center of the Earth. Okay, so this kind of problem is a good example of how we can take what we know about planets, about Earth science, and sort of apply it in a thought experiment to figure out what might have happened 2 billion years ago. All right, so as always, for all of these things, if you have questions, please feel free to email me or stop by office hours and we can talk through some of this. Don't forget your quiz due tonight if you haven't done it, and send me your ICA from today when you get that done. I will see you on